For decades, the SR-71 Blackbird ruled the sky, cruising at Mach 3.2, about 2,200 miles per hour. It was so fast that thousands of missiles fired at it never scored a single hit. For half a century, nothing came close. Now something faster is coming, the SR-72 Darkstar. A new stealth aircraft built to push toward Mach 10, nearly 7,700 miles per hour. At that speed, modern air defenses barely have time to react. So the real question is this: how close is the SR-72 to the sky? And will it be airborne in the present war? Why the US wants the SR-72 Darkstar? When a machine moves at Mach 10, the real enemy is not the missile on the ground. The real enemy is the clock. By the time a radar operator sees a track, checks it, calls a commander and gets permission to fire, that aircraft can already be hundreds of miles away. Mach is just a way of saying how many times faster than sound something is. At high altitude, 1 Mach is roughly 760 miles per hour. The point is simple. This kind of speed cuts the enemy's reaction time down to almost nothing. The United States has chased that kind of edge before. During the Cold War, it built a spy plane that was so fast and so high that it might as well have come from another world. This was the SR-71 Blackbird, built by a secret group inside Lockheed called Skunk Works. The Blackbird cruised at about Mach 3.2 and often flew higher than 85,000 feet. At that height, the sky above the cockpit looked black even at noon, and pilots could see the curve of the Earth under them. They wore pressure suits closer to astronaut gear than to normal flight suits because the air was so thin that a simple cockpit leak could be deadly. Speed and height were not just party tricks. They were the main defense. During its service life, more than 4,000 surface-to-air missiles were fired at the SR-71 by countries desperate to knock it down. Not one of those missiles scored a kill. Every Blackbird that was lost went down to accidents and technical problems, not enemy fire. The tactic was simple and brutal. When warning lights in the cockpit showed a launch, the crew did not dive or hide. They lit the afterburners, climbed, and let the jet run until the threat fell away behind them. The missile might have been faster in a straight line, but it could not stay in the air as long. That record turned speed itself into a kind of armor and made the SR-71 a moving problem for every radar and missile battery on the ground. If you could not hit it, you could not stop it from taking the pictures it came for. But the world that aircraft flew over does not exist anymore. When the Blackbird entered service in the 1960s, most air defense systems were built around single radars and one group of missiles. If you knocked out one radar or flew around one bubble of coverage, you could often slip through. In the 1990s, another shift came with stealth aircraft like the F-117 Nighthawk and the B-2 bomber. They were shaped and coded to reflect very little radar energy back to the sender. For a while, that stealth cloak gave the United States a near-perfect way to kick in the door of defended airspace. Other countries did not sit and accept that. Russia and China spent decades building thicker and smarter defenses. They fielded long-range systems like the Russian S-400 and now the S-500, and the Chinese HQ-9 family, which are not just single launchers but part of full networks. In a modern integrated air defense system, many radars, command posts, and missile launchers are tied together by data links and computers. One radar can spot a target, another can track it, and a launcher far away can fire based on that shared picture. At the same time, those same rivals started building their own very fast weapons. Russia has the Avangard hypersonic glide vehicle, which can ride on top of an intercontinental missile and then maneuver at very high speed in the atmosphere. China has the DF-17, a medium-range missile built to carry its own hypersonic glider. Both are designed to be hard to track and hard to intercept because they do not fly in a simple high arc like older ballistic missiles. All of this changes the basic math for any slow or even medium-speed aircraft that tries to fly into that kind of airspace. The old formula was simple: fly high, use stealth to be hard to see, use jamming pods to confuse radar. Now the radars look farther, see more types of targets, and feed their data into smart networks. The result is that the comfortable safety bubble that American aircraft once had over hostile ground is getting smaller every decade. This fear pushed the United States to explore what it once called prompt global strike. The goal was to hit almost any target on Earth with a conventional non-nuclear weapon in about an hour from the moment the order is given. Today, that effort lives on under names like Conventional Prompt Strike and includes hypersonic missiles launched from ships, submarines, or land batteries. The most aggressive version of that idea is a reusable aircraft that can sprint across continents, find targets in real time, and either strike them itself or hand their exact location to other weapons. That is where the SR-72 concept, often nicknamed Darkstar or Son of Blackbird, comes in. Around 2013, Lockheed executives publicly floated the idea of a new hypersonic aircraft that would pick up where the SR-71 left off. On paper, it would be a strategic intelligence, surveillance, and reconnaissance platform. In plain words, a high-speed spy aircraft that can also carry weapons. Open sources describe it as a design that would cruise around Mach 6, roughly twice as fast as the old Blackbird. Unlike the SR-71, which always needed 2 humans on board, the SR-72 family is meant to be unmanned, or at least optionally piloted. At those speeds and heights, the human body becomes a limiting factor. If you do not have to keep pilots alive and conscious, you can push the aircraft harder and focus its entire design on speed, altitude, and sensors. The role is also broader. Instead of only taking pictures and electronic readings, the SR-72 is meant to be able to cue weapons or even launch them, blurring the line between spy plane and bomber. What separates this concept from a simple hypersonic missile is the word reusable. A missile is a one-way trip. It leaves the launcher, flies its path, and ends its life in a blast. A hypersonic aircraft is meant to take off from a runway, carry its payload, do its job, come back, and then do it again. It can loiter outside dangerous airspace and dash in when needed. It can also shift from one hotspot to another during a single long mission instead of being tied to one target. Take the distance between Washington, District of Columbia, and Moscow. The straight-line distance is a little under 4,900 miles. At a cruising speed near Mach 6, or about 4,600 miles per hour, a high-altitude aircraft could, in theory, cover that distance in just over an hour. The path from Los Angeles to Tokyo is a little under 5,500 miles. The same class of aircraft could, on paper, make that flight in roughly the length of a normal movie. This speed is not just about hitting fixed points. It changes the kinds of missions that become thinkable. A hypersonic spy and strike aircraft can be based far from the front lines and still get eyes on a crisis area before a mobile missile launcher has time to move very far. If satellites spot unusual activity at a launch site, a platform like this could race in, confirm what is happening, and either pass back exact coordinates or deliver its own weapons before the target can hide under a tunnel, a hangar, or camouflage. It also rewrites how support for other forces could work. In a major conflict, slower bombers or cruise missiles might be heading toward a cluster of air defenses. A hypersonic aircraft could rush ahead of them, scan for radars that turn on, and feed targeting data back to standoff weapons. Those slower weapons would not have to waste time searching or risk flying directly over hidden batteries. They would arrive already knowing where to aim. On top of that, a platform that fast and reusable casts a long psychological shadow. Leaders who know that a foreign power can reach almost any important site in their country in under an hour start to think differently. They have less time to move high-value assets. Building a machine that can live at those speeds without tearing itself apart is the hard part. Inside the SR-72 Darkstar. Once you push an aircraft into hypersonic speed, the main threat is not a missile or a gun. The main threat is the air itself. At those speeds, the air in front of the nose is squeezed so hard and so fast that it turns into a white-hot wall of heat. Every inch of the skin has to fight that heat and survive it for hours, not seconds. That is the brutal world Darkstar has to live in. Think about the nose, the wing edges, and the air intake of a very fast aircraft. As the speed climbs, the air right around those parts can reach temperatures hotter than a blast furnace. Some research has shown that in extreme high-speed flight, the air near the front of a vehicle can reach several thousand degrees Fahrenheit, more than hot enough to melt normal metal in a short time. At around Mach 6, the outer skin and leading edges are dealing with heat that can climb well above 1,800 degrees Fahrenheit if they are not protected. The main enemies are simple. The first is air rubbing and slamming along the surface, which heats the outside. The second is air being squeezed inside the intakes, which heats everything that feeds the engine. That heat problem is why a normal jet engine is useless for true hypersonic flight. A regular fighter or airliner engine is a turbine. It pulls in air, slows it down, squeezes it with spinning blades, mixes it with fuel, and burns it. That works well up to about Mach 2 or maybe a little above that. Past that point, the air that reaches the compressor is already so hot and so squeezed that the metal blades start to get close to their limits. If you tried to push a normal turbine toward Mach 4 or Mach 5 for long stretches, the core would not last. At the other end, there is a different kind of engine called a ramjet and a scramjet. Both have no big rotating compressor. They use the speed of the incoming air itself to squeeze it. In a ramjet, the air is slowed down below the speed of sound before you burn the fuel. In a scramjet, which is short for supersonic combustion ramjet, the air stays faster than sound as it passes through the engine. That sounds wild, but it has one huge catch. A scramjet only works well once the vehicle is already moving very fast, around Mach 4 or more. Below that, the air is not compressed enough for a clean burn, and the engine will not make useful thrust, so there is a gap. Turbines are good at low and medium speeds, but start to overheat and choke at the high end. Scramjets are great at very high speeds, but are almost dead weight when sitting still or moving slowly. You cannot light a pure scramjet on the runway and roll off like a normal jet. That leads to the key question behind Darkstar. How do you build one power system that can act like a normal jet engine when you are taking off, and like a scramjet rocket when you are tearing across the upper atmosphere? The answer the United States has spent years studying is called a turbine-based combined cycle engine. That phrase sounds complicated, but the idea is simple. It is one engine system that has two faces. One face is a turbine for low and medium speeds. The other face is a ramjet or scramjet flow path for hypersonic speed. Both sides share the same air intake and the same exhaust, but they work at different times in the flight. NASA and Lockheed worked under government study contracts to see if this kind of engine could really fit into an SR-72 type aircraft. On the runway, and in the first part of the climb, the combined engine breathes like a normal fighter jet. It pulls in air, slows it down inside, and uses a turbine core to spin compressors and drive the exhaust out the back. The aircraft rolls down a normal long runway, lifts off, and climbs through subsonic and then supersonic speeds just like any other high-performance jet. The pilots or the onboard computer do not have to light any rockets or strap the aircraft to a booster. As the speed climbs through the high supersonic range, somewhere around Mach 3, the engine starts to change its inside path. A set of doors and ducts begin to send more of the air around the turbine core and into a second channel. In that channel, there are no fragile compressor blades. The air is slowed a bit and squeezed by the shape of the ducts and shock waves, not by spinning metal. Fuel can start to burn in this stream while it is still moving very fast. Once the aircraft is fast enough, around Mach 4, the turbine side can shut down almost completely. It is no longer adding much power. At that point, the scramjet part becomes the main driver. The air comes in at hypersonic speed, gets squeezed and heated by the shock at the inlet, and then mixes with fuel in a region where the flow is still faster than sound. The burning gas, then, rushes out the back and pushes the aircraft forward. If all of this sounds like a juggling act, it is. Switching from one mode to another without a stall or a backfire is one of the hardest parts of the whole project. Now move away from the engine for a moment and look at the body of the aircraft. At hypersonic speed, the whole skin is under attack from heat, not just the hot parts inside. Even at lower speeds, the old SR-71 had to be built almost entirely from titanium alloys, which could handle much higher temperatures than normal aluminum. At cruise, the SR-71 airframe would heat up and expand so much that some gaps in the panels only sealed fully once the aircraft was at speed and hot. Its special JP7 fuel was not just used to make thrust. It also ran through pipes around hot areas to act as a liquid heat sponge before it got to the burners. For something like Darkstar, the problem is even worse, because Mach 6 flight lives in a much hotter range than the Blackbird ever saw. At those speeds, titanium on its own starts to struggle. That is why modern hypersonic research looks hard at carbon-carbon composites and ceramic matrix composites. Carbon-carbon is a material made from carbon fibers baked into a solid block and then treated until it can hold its strength at very high temperatures. It has been used on leading edges and nose caps of hypersonic vehicles because it stays strong at temperatures where many metals would soften or melt. Ceramic matrix composites are related materials that mix ceramic and fibers to get a shell that does not crack easily and can handle repeated heat cycles. These kinds of materials are now seen as some of the best options for the hottest spots on hypersonic aircraft. A likely approach for a hypersonic aircraft body is a hot outside and a cooler inside. The outer skin and leading edges are built as a hot structure, meant to glow and run at very high temperatures without failing. Under that shell sits a colder inner frame that holds the fuel, the crew cabin if there is one, and the main equipment. Between the two, designers can place special blankets or tiles that slow down the flow of heat. The goal is not to keep the surface cold. The goal is to keep the important inner parts within safe limits, while the outside can ride in a sea of fire. Fuel will almost certainly be used as a cooling fluid again. Just like in the SR-71, the fuel for a Darkstar-type aircraft can be pumped through small channels that snake through hot areas before it reaches the engine. In newer designs, those channels do not have to be straight pipes. With modern metal three-dimensional printing, parts of the engine, wings, or inlets can be built layer by layer with tiny coolant paths already inside them. That means fuel or another fluid can flow very close to the outer skin, soak up heat, and then carry that heat away to the engine, where it is turned into thrust instead of damage. It is like giving the aircraft a system of veins just under the skin, filled with cold fuel instead of blood. All of that solves how to push and cool the aircraft. There is still the question of who or what is steering it. At hypersonic speed, even tiny delays start to matter. When control signals are sent through satellites, there's always a small delay. The radio signal has to travel up to the satellite, come back down to the aircraft, and then the response has to make the same trip back again. In normal flight, that delay is not a big deal. At several thousand miles per hour, the aircraft can move a long way in that short pause. If a human on the ground had to watch a screen and move a joystick to correct every bump, the aircraft would likely be lost. That is why most serious plans for an SR-72 type machine treat it as unmanned or at least as partly unmanned. The idea is that a very strong onboard computer using forms of artificial intelligence would handle the instant-to-instant work. It would keep the aircraft stable in thin, hot air. It would manage the engine mode, watching for any sign of a stall or a shock wave moving out of place. It would take sensor data from cameras, radar, and other gear and keep the aircraft on the planned path even if conditions changed. If something went wrong, like a sudden drop in pressure in one intake, the system would react in tiny fractions of a second, long before a human could even say what happened. Humans would still matter, but their job would move up a level. They would choose the route and the mission. They would set the rules for what the aircraft is allowed to do and not do. They would decide whether to approve weapon release. The machine would decide how to stay alive while carrying out those orders at a mile per second. Once a pass is done, the aircraft does not hang around. It stays at high speed only as long as needed, then begins to trade speed for safety and fuel. The engine eases back out of scramjet mode. More flow goes back through the turbine path. The vehicle sinks into thicker air and lower speeds where the skin can slowly cool. By the time it comes back toward friendly airspace, it is once again flying like a very fast but normal jet, headed for a runway, a fresh load of fuel, and the next task. So, how much of all these has moved from drawings and test beds into metal, carbon, and working engines? Is the SR-72 Darkstar already flying? The United States has a habit of flying new warplanes in secret for years before anyone outside the program even knows their names. Back in the 1980s, a strange black jet called the F-117 was already flying combat test missions long before the public got a single clear photo. It first flew in 1981, but the government did not admit it even existed until 1988. For 7 full years, it was hidden behind fake cover stories and night flights out of remote desert bases. That pattern never really went away. Stealth bombers, new fighters, odd shapes caught on satellite photos in the desert, again and again. The rule has been simple. By the time the world learns the official name of a new aircraft, the people who fly it have already been living with it for a long time. So when we talk about a Darkstar class machine, the uncomfortable truth is that if something like it is real, we are not supposed to know yet. The first real hints of a son of Blackbird go back to the late 2000s. Around 2007, defense writers started picking up whispers that Lockheed Martin and its secretive Skunk Works team were studying a new high-speed spy aircraft that could fly much faster than the old Blackbird. At that point, it was not a program, just a set of studies and ideas. In 2013, Lockheed broke cover, at least a little. In an interview and later slides, company officials talked openly about something they called SR-72, a notional Mach 6 reconnaissance and strike aircraft that could follow the SR-71. They described it as a long-term goal, not a signed military contract, and hinted that a smaller demonstrator might fly in the late 2010s or early 2020s. The next year, NASA funded a study with Lockheed and engine company partners to look at advanced propulsion for exactly this kind of aircraft. In simple terms, the study asked whether one air-breathing engine system could carry a vehicle from takeoff to very high-speed cruise using only the air around it. In 2017, a senior Skunk Works leader said in an interview that if the funding and technical pieces lined up, a technology demonstrator could fly in the mid-2020s. That line, more than anything, is what started the wave of headlines saying SR-72 could fly by 2025. But it was a hope, not a promise. And as of early 2026, there is still no public proof that such a demonstrator has flown. Open sources agree on one hard fact. There is no confirmed flight test of an SR-72 and no government statement saying, "This aircraft is now in service. This aircraft is now in service." That does not mean nothing is happening. You have to look at the money. In recent years, Lockheed's own financial reports and filings have quietly mentioned very large losses on a single classified fixed-price contract inside its aeronautics business. One filing in 2024 noted cumulative losses of about $335 million on that secret program alone, tied to highly complex design and systems integration work. For a normal company project, that kind of loss would be a disaster. For a long-term government contract, it usually means something else. The customer is pushing for cutting-edge hardware, the contractor underbid the work, and now the real cost of solving all the hard problems is showing up. Outside analysts have connected these overruns to a small group of unknown aircraft programs. Some point to a sixth-generation fighter effort, some point to a long-range drone, and some argue that this is exactly the sort of line you would expect for an SR-72 type demonstrator. None of that is confirmed. What is solid is that a very expensive, very advanced flying system is being worked on in secret, and it lives in the same part of the company that handled the Blackbird and the stealth fighter. Now look at where that work would take shape in metal. Out in the Mojave Desert, at Air Force Plant 42 near Palmdale, California, Skunk Works opened a new factory building in 2021. It is called Building 648. Lockheed describes it as an intelligent, flexible factory of about 215,000 square feet, built from the ground up for secret aeronautics programs. Inside, Every major tool and station is tied into the same digital system, from design screens to robotic drills and automated inspection gear. The key idea there is something called a digital twin. In plain terms, this is a complete computer copy of the aircraft and the factory process. Engineers can tweak the virtual plane, stress it, heat it, and build it over and over on screen until they are happy, before they ever cut a real piece of metal. For a very fast aircraft that has to deal with huge heat, tight fuel margins, and complex control laws, that kind of virtual dress rehearsal is almost required. Skunk Works has been growing its staff at Palmdale and pouring money into this single site. Company leaders say this allows them to cut build times in half and bring more than one new design online at the same time. Taken together with the cost overruns on that unnamed program, it paints a picture. A big, long-term, high-risk aircraft project is underway in the Black World, and it is important enough that the company built a new digital factory mainly to support it. Then there is the part where Hollywood walked into the story. In 2022, the film Top Gun. Maverick opened with a sleek, needle-nosed jet called Darkstar that is supposed to reach Mach 10 before it breaks apart. The producers did not just make up that shape in a back room. They went directly to Skunk Works. Engineers and artists from the same team that works on real secret aircraft helped design the movie jet, and a full-size mock-up was built and filmed at a real test range. Lockheed later stressed that the Darkstar in the movie is not a real aircraft and is not a one-to-one copy of any current project. But they also admitted that it borrows lines and ideas from real hypersonic research. The nose shape, the low blended body, and the engine inlets all look like something that has spent time in a wind tunnel. According to one widely repeated story from a producer interview, the mock-up looked so convincing on a runway that Chinese intelligence retasked a spy satellite to get a closer look when it was sitting out in the desert for filming. Whether that satellite story is fully true or a bit of show business bragging almost does not matter. The bigger point is that the boundary between fiction and reality is now very thin. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.